If we have n random variables, x1 through xn, and we have a function of n variables, that is, its domain is Rn and its codomain is R, then I can create a composition of this to create a new random variable z, which is the function of these random variables. An important special case is the case when g is linear. So if g, which is a function from Rn to R, is a linear function of n variables, then I can write it as an intercept plus a constant times x1 plus another constant times x2 plus and so on, and a final constant bn times xn. So if I create a linear function of my n random variables, giving me the same expression but with random variables instead of ordinary variables, then we say that our random variable y is a linear function of the n random variables x1 through xn. It turns out that a linear function of random variables has special important properties, and the first one is the expected value of y. We have the following result, which is of tremendous importance in probability theory. If I create y as a linear function of n random variables, then the expected value of y will come out to be the same linear function evaluated at the expected values of the corresponding xi. So the way you typically see this is in the following form. The expected value of this linear function is a linear function of expectations. Another expression that's common is to say that we can move the expectation operator inside a linear function. It is then important to remember that in general we cannot move the expectation operator inside a nonlinear function. So for example, if I have a product instead, x1 times x2, which is not a linear function of x1 and x2, then this will in general not be equal to the product of the expectations. In addition to a very nice and useful formula for the expected value of a linear function, we also have a result for the variance of a linear function of random variables. But this formula requires one additional assumption, and that is independence. So if these random variables are mutually independent, then we have a nice formula for the variance of a linear function of these random variables. And the formula on the right hand side, well, the first thing we see is that the result on the right hand side contains no a. A will disappear as it is a constant, and constants don't have a variance. The variance on the left hand side will become equal to the variance of b1 x1 plus and so on all the way to the variance of bn xn. We already know that when we look at the variance of a linear function of a single random variable, like the first term here, we can take this constant outside if we square it. That's why we get b1 square variance of x1 plus all the way to bn square variance of xn. The final thing I want to say about the variance formula is that independence is a sufficient condition for this formula to hold. It will actually hold under weaker conditions, such as these random variables being uncorrelated, and that's something we'll look at later. Here is a simple example. x1 through xn are n mutually independent random variables. The expected value of each of the random variables is equal to mu. They all have the same expected value. The variance of each random variable is equal to sigma square. Then the expected value of the sum of these random variables will be equal to, and note that we don't need the independence assumption for this, expected value of x1 plus all the way to expected value of xn. Each one is equal to mu, so it's mu plus mu plus mu plus mu n times, and it comes out to be n times mu. Similarly, the variance of this sum is then equal to there is actually a 1 in front of x1, and 1 squared will still be 1. So it comes out to be variance of x1 plus all the way to variance of xn. Each random variable had a variance of sigma square, so it's sigma square added n times, and that comes out to be n times sigma square.